Welcome back. In the second half of this lecture, we're going to now be putting together all of our clues, intercepts, behavior at the intercepts, and behavior in order to graph our polynomials. So let's start off with this polynomial that we have here. Notice that this polynomial is already factored for us. And that's sort of a foreshadowing for the future sections of this course. I'm not always going to give us polynomials that are factored, and so part of what we'll be doing in Chapter 5 will be talking about how do we factor polynomials when they're not just a nice little quadratic. When they're bigger than that, how do we get it into factored form? So that's something to look forward to, but for right now we've got our nice factored polynomial, which means if we wanted to think about graphing it, we need to, number one, first start thinking about x-intercepts and y-intercepts. And for the x-intercepts, we just need to solve where is it equal to 0. So we're letting g of x be equal to 0, and that means we'll have x cubed times x minus 2 squared times x plus 1. All of that's equal to 0. That means x cubed is 0, or x minus 2 squared is 0, or x plus 1 is 0. And we can come up with our x-intercepts of 0, of 2, and of -1. Okay, so that's the first part. We've got our x-intercepts. Our x-intercepts are 0, 0, 2, 0, and -1, 0. The next thing that we need to think about is the behavior at those x-intercepts. So this is where we're going to need to now think about multiplicity and all the rest. Remember that for the behavior at the x-intercepts, it depends only on the multiplicity of those factors. So if we're thinking about making ourselves a little bit of a table of our zeros, our multiplicity, and our behavior, we had 0 was one of the zeros. And if we go back and look, we can see that 0 came from x cubed, which has a multiplicity of 3. So that means that the 0 of 0 has multiplicity 3, odd multiplicity, which means it's going to cross the x-axis. If we look at x being 2, that came from x minus 2 squared, so multiplicity of 2, and that means we're going to touch the x-axis. And then finally, the last 0 that we have was a 0 of -1, and that came from x plus 1, not raised to any powers, so multiplicity of 1. So our 0 of -1 has multiplicity of 1, and that means we're going to cross the x-axis. Okay, so that's part of our work that we have. The other part that we'll need is the y-intercept. We'll also need to find the end behavior, and for that, of course, we'll need to know what the leading term is. So let's do that over here. I'm just going to divide the screen up, and let's think about our leading term. Our leading term, of course, we get that from multiplying the leading terms of each of our factors. So our leading term we have, there's x, which is cubed. Then we have the x from x minus 2, which is squared. Then we have the x from x plus 1, not raised to any powers. That would be a leading term of x to the power of 6. So if we're thinking about our end behavior, that would be the same as the graph of y equals x to the 6, which, if we're remembering our power functions from back in section 5.2, x to the 6 looks just like x squared in that it goes up to positive infinity on both sides. Now there's one other thing that I might want to find here, which is my y-intercept. So I said that, we found our x-intercepts, we've talked about their zeros and the multiplicities of them and their behavior. The one thing that we haven't found is the y-intercept, which, if we're really thinking about it, we actually already have. Remember that our point that we had 0, 0 was an x-intercept, but that's also a point that's a y-intercept as well. Because, of course, if you have the point 0, 0, then that means you're on the x-axis and you're also on the y-axis. The other thing to remember, of course, here is that for any function, you can't have more than one y-intercept. And that's because if you had two different y-intercepts, that would mean that you would fail the vertical line test. You wouldn't be a function. So one thing that's kind of nice is if you know that you've got one y-intercept, then that must be the only y-intercept. So I already know that 0, 0 is a y-intercept, and because we're talking about a function, it must be the only y-intercept. Okay, so now we just need to put things together. So what we'll do will be to first plot our zeros. So our zeros are at 0, 2, and -1. So we have one at 0, one at 2, and one at -1. And the first thing that I always start off with is putting in my end behavior. So if we're looking back to our end behavior is that the graph goes up to the far right, and on the far right and the far left, it goes up to positive infinity. So when I'm plotting this, then on the far right, after my furthest to the right x-intercept, and after my furthest to the left x-intercept, I must be going up to infinity for both. Now, the other thing to mention here is, of course, that our clues that I've generated here, all of my little facts that I have about my zeros, the behavior at them, the end behavior, the y-intercepts, none of those should contradict each other. If they do, if I can't make the graph fit in all of my facts, then that means I've made a mistake somewhere along the way, that all of my facts that I find about end behavior should match up with the facts that I find for my zeros. So for my zeros, I'm looking at I need to cross the x-axis at 0 and at -1, and I need to touch the x-axis at 2. So I need to cross the x-axis at 0 and -1, and I need to touch the x-axis at 2. So crossing and crossing and touching. There we go. So we can see it's not the most smoothly drawn graph that I've ever done, but this shows that we do have the end behavior that we predicted to positive infinity on the far left and on the far right. We crossed at -1 and at 0, and we touched at 2. And so since I was able to make all of my clues fit together, then I can feel confident and say that this must be my function. Now, as far as labeling things go, there's not really much to label here because all of my x-intercepts, they happen to be at tick marks along the x-axis, so I don't need to label their coordinates. The only thing really that I should be labeling is my function itself. So I would probably just think about labeling my function just as we had it labeled there, g of x being x cubed times x minus 2 squared times x plus 1. The one thing that I will not be able to do, and that's in case you're wondering about these, how high up is this point? How far down is that point? I have no idea. Well, actually I do, because I've got the calculus skills to be able to find out if I want to. But for us, we really won't be able to tell. So here, I'm just doing the general shape of the curve. Does the graph actually have a y value of 2? Does it have more of a y value of 4? or more of a y value of 50. Who knows? That's something that you won't be able to tell, unfortunately, not until you get into a calculus class. So same thing is true for the minimum value here. How far down is it? Is it down to -2? Is it only very shallow? Is it very deep? Who can say this is the best that I'll be able to do with the skills that we have for this class? So that means my turning points, I can't really label them or get a good idea as to where they are. The only thing that I really do know here is the location of my x-intercepts. Let's do another one. And so here we've got our polynomial, which has already been factored for us. And if we're thinking about this, and we're going to do this one a little bit speedier, let's just start by making ourselves a table of values for our zeros, our multiplicity, and our behavior. So if we're looking at our zeros, we have zeros of 0. That has a multiplicity of 2, which means that there we're going to touch the x-axis. And then for all the other factors, they all show up exactly once. So the rest of them, their zeros, will all have a multiplicity of 1. If we look at where are they equal to 0, 2x minus 1 is 0 when x is a half. Multiplicity of 1, so we cross the x-axis. Negative a half, same thing, multiplicity of 1, so we're crossing the x-axis. X minus 3, the 0 is 3, with multiplicity of 1, crossing the x-axis. And x plus 3, well, that's equal to 0 when x is -3, multiplicity of 1. Yet again, we're crossing the x-axis. So we're crossing the x-axis everywhere except for at 0. We've got all of our x-intercepts, 0, 0, half 0, -half 0, 3, 0, and -3, 0. We also have that 0, 0 is also a y-intercept, so I don't need to find y-intercepts in addition to x-intercepts. And the last thing that I need is my end behavior. And if we're thinking about our end behavior, that'll be the same as the behavior of our leading term. And if we're looking at our leading term, that's 4x to the 6. Our leading term is 4x to the 6, so our graph will have the same end behavior as 4x to the 6, which goes up to the far left and to the far right on both sides. So now we've got all of the things that we need in order to be able to graph our function. And so let's get into that, and let's start by first plotting our points. We have 0, we had a half, negative a half, we had 3, and -3. And so what did we have? We had that 3 and -3, those were our furthest away x-intercepts. And so from them, that's where our end behavior begins. And we know the end behavior is to go up to positive infinity on either side. We know that at all of our x-intercepts, except for the origin, that's the only one where we touch, all the other x-intercepts we cross. So at -3 we cross, and at 1 we cross, and at 0 I touch, and at a half I cross, and at 3 I cross again. So I crossed at 3, 1/2, -1/2, and -3. The only place where I touched was at 0. And now I do need to label a couple of these, the points 1/2, 0, and the -1/2, 0. Those aren't at tick marks, so I do need to label them. But the 0, 0, 3, 0, and -3, 0, I don't need to label them. And now if I want to just label my function I'll label it as, this is where I'll need to go back and remind myself of how the function was labeled or how it was written out. I could either use the factored or the unfactored version. I'll use the unfactored version to label it. It's a little bit more compact. So we have that our graph is 4x to the 6 minus 37x to the 4 plus 9x squared. There we go. There's our function f of x. One thing that we could do if we felt like it is to just look at symmetry here for a minute. The way that I've drawn it makes the graph look like it's symmetric around the y-axis. And if you do take a spare minute, you can confirm that f of x is an even function. And so that actually does work out, that yes, our graph should be symmetric around the y-axis. Just a nice little thing to think about here, a nice way to connect our previous material with what we're working on now. Okay, so now what we need to do is come up with a polynomial function that has this shape of a graph. You'll notice here I haven't bothered to label the y-axis here with any tick marks, and that's of course because I don't know how high up or how low these minimum or maximum values are, and I don't want us to try to guess or need to guess. I just want to come up with a polynomial that has roughly this kind of a shape. And by this kind of a shape, I mean, for example, for A, that the end behavior is going up on the far left and on the far right, and that it has zeros at -2, 0, and 3, that at 2 of those x-intercepts you're crossing, and at 1 of the x-intercepts you're touching. So I want us to be able to put in all of those facts together and then come up with a reasonable polynomial function that should have that shape. So I'll start building this one beginning with the zeros. So I know that x minus 2, minus 2 is a 0, so x plus 2 should be a factor. And since it's crossing through there, then it should be a factor with an odd power. Power of 1 is an odd power, so x plus 2, I'll have that being a factor. I also have that x being 0 needs to be an x-intercept, so x needs to be a factor. Again, it's got to have an odd power to it because it's crossing through the x-axis. So x to the power of 1 is fine, or x to the power of 3 or any other odd powers is fine. And then finally, at 3, we want to touch the x-axis. So x minus 3 needs to be a factor, and it needs to be a factor with an even multiplicity because we're supposed to touch the x-axis at that point. Now, one thing that you can quickly check on this one here is that f of x, as I've written it, this has a leading term of x to the 4, which means that the end behavior should be the same as the end behavior for x to the 4, going up on the far right and on the far left, which matches exactly what our graph is doing. So I can feel happy with what I've got, because with what I've got, it does have the same end behavior as the given function, and it also has the same x-intercepts as the given function, and it also has the same behavior as the given function. Let's do the same thing with g, or with part b, which I'm going to call g of x. So we've got a couple of zeros here. We've got a 0 at -1. So I want x plus 1 to be a factor. And it needs to have even multiplicity since we're touching, so I'll square that. We need to be crossing the x-axis at x being 1. So x minus 1 needs to be a factor and with odd multiplicity so that you cross. And then at 2, we need to touch the x-axis but not cross. So x minus 2 needs to be a factor, but it needs to be a factor with even multiplicity so that we touch but don't cross. And if you were to look at the end behavior of this function, the leading term would be x to the power of 5, which means that the end behavior would be going up on the far right and going down on the far left, which is the opposite of what we want. Here we want to be going up on the far left and down on the far right. And of course, an easy fix to that is if I were to multiply my function by a negative, so -2, for example, that would mean that my leading term would no longer be x to the 5. My leading term now would actually be -2x to the 5, which would mean that we would have the same end behavior as -2x to the 5. You'd be going down on the right and up on the left, which now this matches with what I have. So this function g of x that I've created, it has the correct end behavior. It does go up on the far left and down on the far right. And it does behave in the correct way at all of the x-intercepts that we have. X-intercepts of -1, 1, and 2, touching at -1 and 2, crossing through at +1. So I can feel confident, and I can say that this function that I've created for myself, g of x, that would be something that has the same shape as the function that we've got graphed in part B. The last little thing to mention here, and it's a nice little theorem, and you'll see this again in calculus if you take calculus next, the intermediate value theorem. And this is a nice little consequence of graphs of polynomials. If you're remembering from back in 5.2, I said one nice feature of a polynomial function is that its graph is continuous. That means that there's no breaks. It doesn't suddenly start jumping around and skipping around, that it's all one nice connected smooth piece. And because of that, if you know that somewhere for your polynomial you're above the x-axis and somewhere else you're below the x-axis, then in between those 2 points you have to cross the x-axis. That's the intermediate value theorem. It's telling you that if you have two y values for a polynomial that have opposite signs, so if there's one point where you're above the x-axis and one point that you're below the x-axis, well then you must have a real root. You must cross the x-axis somewhere between those two x values. So for something like this, f of x is this polynomial. If I want to show that it has a real root somewhere between 0 and 1, it's easy enough for me to show that if you look at f of 0, what is the y value when x is 0? That would be -1. How about when x is 1? Well, the y value would be 3. So you know, for example, that you've got the point 0, -1. You've got the point 1, 3. And since a polynomial is nice and smooth, that means that as you make your way from the first point to the second point, at some point in the middle, you'll need to cross the x-axis. So I can say here that by the intermediate value theorem, you can say that f of x is equal to 0 at some point between x being 0 and x being 1. So somewhere in that interval from 0 to 1, you must cross that x-axis, because for the lower end of it, you're below the x-axis, and at the end of the interval, you're above the x-axis. So somewhere in the middle, you must have crossed the x-axis. And that's true for any polynomial function, because polynomial functions are nice and continuous. No breaks, no holes, no jumps, no skips.